We usually think of numbers like pi, e, or the golden ratio as just digits we were forced to memorize for a high school test. But they aren't just abstract concepts, they dictate the swirling geometry of rivers, the physics of a spider web, and the biological packing algorithms of a sunflower. Today, we are going completely under the hood to look at the raw, hard-coded values that hold the reality together. We are going to visualize the absolute beauty of mathematical constants and show you exactly where their code is executing in plain sight. Alright, let's start with the most famous number in the universe, pi, or 3.14. At its core, pi is just the ratio. If you take any circle, a steering wheel, a planet, or a single circular particle rendered on screen, and measure the distance around the outside, then divide it by the distance across the middle, you always get pi. But how do we actually model it mathematically without just measuring things? If we want to compute pi from scratch, we can use a highly visual trick called the Monte Carlo method. Imagine a two-dimensional square canvas with a circle perfectly fitting inside it. If you write a quick script to randomly fire thousands of points or pixels at this canvas, some will land inside the circle and some will land outside or to the corners of the square. If you take the number of pixels that landed inside the circle, divided by the total number of pixels on the entire canvas, and multiply that result by 4, you get pi. As your particle count approaches infinity, your output logs onto 3.14159. Interesting, isn't it? But here is where it gets wild. Pi doesn't just live in a perfect geometry, it leaks out into the real world. Think about rivers. If you pull up a satellite graphic of a river, like the Amazon or the Mississippi, and measure its total winding, curving length, and then divide that by the straight line from its source to its mouth, guess what number you get? On the average, the sinuosity of unconstrained rivers on Earth approaches pi. The physics of fluid dynamics naturally curls waterways into the mathematical equivalent of a circle. Next up is 1.618, better known as phi, or the golden ratio. If pi is the number of circles, phi is the number of beauty and extreme biological efficiency. Mathematically, it is pretty simple to define. If you take a line and split it into two pieces, the ratio of the whole line to the big piece is exactly the same as the ratio of the big piece to the small piece. The perfect infinitely scaling proportion is 1.618. But if we want to model it mathematically, the easiest way is to use a simple recursive loop, the Fibonacci sequence. You start with 1, then 1, and just keep adding the last two numbers together. 1, 2, 3, 5, 8, 13, 21, and so on. If you take any number in that sequence and divide it by the one right before it, the result gets closer and closer to phi. Visually, if you render out squares with those exact Fibonacci dimensions next to each other, they form a perfect golden rectangle. Draw a smooth quarter circle curve through the opposite corners of each square, and you have just generated the golden spiral. But here is the coolest part about where this shows up in real life. Nature is essentially running a highly optimized spatial packing algorithm to save space and gather maximum sunlight. If you look closely at the center of a sunflower, the seeds aren't just thrown in randomly. The plant grows a new seed in the center, rotates exactly 137.5 degrees, which is known as the golden angle derived directly from phi, and grows another. This highly specific irrational rotation ensures the seeds never stack up in straight, inefficient rows. Instead, they form those tightly packed interlocking spirals. It is essentially a biological rendering engine using 1.618 to calculate maximum density without wasting a single pixel of space. Next, let's talk about a number that shouldn't exist. I, the imaginary unit. When we first learn math, we are told you can't take the square root of a negative number. If you square a negative, it always turns positive. But centuries ago, mathematicians decided to essentially patch the system. They invented the number I and hardcoded it so that I squared equals -1. It sounds like a massive cheat, but it accidentally unlocked a hidden dimension of reality. To model this visually, picture a standard one-dimensional number line on your screen. If you take a vector pointing at 1 and multiply it by -1, it flips 180 degrees over to the negative side. But what happens if you multiply it by I? Instead of flipping all the way across, the vector rotates exactly 90 degrees counterclockwise. It lifts off the one-dimensional line completely and drops into a brand new two-dimensional space called a complex plane. Geometrically, multiplication by I is just a clean, perfect rotation function. If you have ever programmed a custom 3D graphics engine, or if you just watch my channel regularly, you know how quickly standard rotation matrices can break down into chaos. Complex numbers and their 3D upgrade, quaternions, are the exact mathematical tools that allows us to smoothly rotate 3D cameras and physical objects in a game world without encountering gimbal lock. We are going to talk about quaternions here, so don't forget to subscribe to stay in touch. This number isn't just a clever rendering trick, it is baked into the actual physics of the universe. Electrical engineers rely heavily on imaginary numbers to calculate the phase shifts of the alternating current that powers your home. Even wilder, in quantum mechanics, the fundamental formula that dictates how subatomic particles move as waves, the Schrödinger equation, physically cannot work without I. To accurately describe the real world, we are forced to use an imaginary number. Moving on to 2.718, known as the Euler's number, or simply E. If pi is the universal constant for circles, E is the universal constant for growth. It is the fundamental speed limit for how fast anything in the universe can compound on itself. To model this mathematically, imagine you write a script to simulate a bank account. You start with $1 and the bank pays 100% interest over a year. If they pay you once at the end of the year, you have $2. But what if you tell your loop to calculate the interest twice a year at 50%? You end up with $2.25. If you crank the loop up to calculate the interest every month, day, second, down to a continuous per frame calculation, you don't get infinite money. The growth mathematically caps out. The hard limit is exactly $2.71828. It is the absolute maximum limit of continuous compounding. Graphically, E has a superpower that no other number possesses. If you draw the function y equals e to the power of x, you get a classical exponential growth curve swooping aggressively upward. But if you measure the slope or the exact steepness of that curve at any single point, the slope is perfectly equal to the curve's height at that exact same point. The area under the curve, it's also the exact same value. It is perfect feedback loop where a system's current state perfectly dictates its rate of change. In the real world, anytime a system's growth depends on how much of it is already there, E runs the physics. It governs the exponential multiplication of cells in a petri dish and the radioactive decay of atomic isotopes. But visually, the best real-life example is a hanging chain. If you hold a rope between 2 points and let it drop under the force of gravity, it forms a shape called the catenary curve. It looks like a standard parabola, but it isn't. The physical droop of a spider web hanging between 2 branches, or the sweeping cables of a suspension bridge. This is drawn using an equation entirely based on Euler's number. Gravity and tension naturally balance out along the geometry of E. And now we reach the grand finale. This is Euler's identity, and it is almost universally considered the most beautiful equation in all of mathematics. Why? Because it takes the 3 seemingly unrelated constants we just talked about, pi, e, and I, and perfectly balances them with the absolute foundation of all numbers, 1 and 0. To model how this works visually, we need to go back to the complex plane, that 2D space we unlocked using our imaginary number I. We already know that E governs exponential growth. Usually, if you raise E to a power, it shoots off into infinity. But if you raise E to an imaginary power, the math breaks out of a straight line. Instead of growing outward, the growth curves sideways. It continuously rotates, tracing a perfect circle with a radius of exactly 1. So how far around that circle do we rotate? That is where pi steps in. Because pi in radians represents exactly half of a full circle, or 180 degrees. When you calculate e to the power of I times pi, your starting point at exactly 1 rotates a perfect 180 degrees along that circle, landing dead center on -1. If you add 1 to that, you arrive back at absolute 0. The constant of continuous growth, the imaginary dimension of rotation, and the geometric fingerprint of a circle all perfectly cancel each other out to equal nothing. This identity is a specific case of Euler's formula, which is the foundational engine of the Fourier transform. Whenever you are breaking down complex wave patterns, like compressing a raw audio file down to an MP3, or writing a shader to render complex ocean waves in a graphics engine, you are using this exact math. It is the tool we use to untangle real-world frequencies into perfectly smooth, computable circles. That will be all for today. If you would like to see more mathematical visualizations, check out this video where we play with shaders. Thanks for watching. Like, comment and subscribe. And if you really like what you saw, consider supporting the channel via membership. See you next time, and ciao!